Hi, we are Group 1 and this is our presentation for Reinforcement Learning module. In this presentation, we will discuss how we evaluated various reinforcement learning algorithms using a simulated lunar landing environment as depicted on this retro-style game console. Here's an overview of what we'll cover.
Problem definition: the lunar lander environment simulates the physics of a space landing. Our goal is to precisely control the spacecraft thrusters to manage its position and velocity, balancing exploration and exploitation to maximize the rewards. We employed several techniques to handle this problem, which are DQN, DDQN, DDPG, and TD3.
Now we'll talk about the methodology of the project. So the first algorithm which we chose was Deep Q network. We particularly chose this algorithm because of its epsilon greedy strategy, which ensures optimal balance between exploration and exploitation, which is really essential for developing and refining the landing strategies. Furthermore, the periodic updates to the separate target network maintain the algorithm's robustness, minimizing fluctuations in the Q value estimates, and also securing consistent learning progress. Altogether, DQN's capabilities make it exceptionally suited for addressing the complexities of the discrete lunar lander task.
DDQN improves upon DQN by addressing the issue of overestimation of Q values. In DDQN, two separate neural networks are used, the online network and the target network. The online network selects actions based on the current policy, and the target network evaluates the selected actions to provide stable targets. The key improvements in DDQN is in the target calculation, while the online network selects the best action. The target network evaluates its value, reducing overestimation and leading to more stable and reliable learning.
DDPG is an off-policy RL algorithm for the environment with continuous action space. It combines concepts from deterministic policy gradient and DQN. Actor-critic approach consists of actor network, which outputs the precise action based on the current state. The second one, critic network, which estimates the value of the action taken by the actor. The advantage of this method leverages both value-based and policy-based strategies, ensuring robust learning and better performance in continuous action environment.
TD3 has three technical modifications: employing twin queue networks to mitigate overestimation bias, updating the policy network less frequently to stabilize learning, and smoothing the target policy with noise to prevent exploitation of queue function inaccuracies. These make TD3 more robust and efficient in complex environments. DDQN's refined update mechanism reduces overestimation bias more effectively than DQN in discrete action requirements. This is shown by a DDQN showing a faster learning rate and higher performance, stabilizing at the reward level of around 250 by episode 600 compared to DQN, which only reaches a similar reward level by episode 1300. DDPG initially struggles with negative rewards but stabilizes at around 250 after 1000 episodes. TD3, benefiting from algorithmic enhancements like twin queue networks and delayed policy updates, experiences a milder initial drop and stabilizes at a higher average reward of around 280 earlier. These mechanisms make TD3 more efficient and consistent, effectively reducing overestimation bias and learning volatility in the continuous action space.
In this project, we applied various reinforcement learning algorithms to solve the lunar lander environment. We also saw the potential of these RL algorithms in solving complex decision-making problems. In our case, the DDQN performed slightly better than the DQN on discrete action space environment, whereas on the continuous action space, TD3 gave better results compared to DDPG. And to conclude things, we obviously gained a lot of hands-on experience implementing and evaluating all these RL algorithms. Thank you.